This is section 5.1, when are figures congruent? Okay, so we're going to start off with a theorem. So we got ABCD theorem on page 252. So if you flip to that, it says every isometry preserves angle measure, betweenness, collinearity, and distance. So basically those are the same exact things that we talked about last chapter. So our isometries are like reflection, rotation, translation, and glide reflection. So if you do one of those movements for an isometry, it's always going to preserve those four things, A, B, C, D. Okay, so that's ABCD theorem. Next thing we've got there is congruent figures. So definition of congruent figures. So it says two figures F and G are congruent figures, written as F is congruent to G if and only if G is the image of F under an isometry. So basically two figures are congruent or look exactly the same if we do like a reflection or a translation or a rotation, something like that. If you take some shape and you flip it or turn it or slide it or something like that, it's going to stay looking like the same exact shape. Okay, so like if I took, say my protractor here, I did a slide of that, it's still going to look like the same exact protractor. It's going to keep its angle measure, betweenness, collinearity, and distance. So the protractor, the original one, and the new one would be congruent to each other because they keep the same size and shape. Now, we actually see this quite a bit in real life, congruent shapes. One example would be like a box of nails or like a box of nuts and bolts. So if you go to the store and you buy a specific size of nail or a specific size of bolt, you want every single one in that box to be exactly the same, because nothing drives you more nuts than taking a nut and a bolt and going to screwing them together and they don't fit with each other. So if you buy a box of nuts and bolts, all of them should be exactly the same size or congruent to each other. Otherwise, when you grab one out of one box and one out of the other box, it's not going to screw together right. Now, there are some errors and stuff when they do manufacturing, where it might be off by a millimeter or something like that. So sometimes they don't always twist together as well as you'd like them to, but they should all be congruent to each other. Same thing if you go to the store and buy like a 12-pack of Mountain Dew. All of those cans of Mountain Dew should be exactly the same size and shape. Okay, you don't want to buy a thing of Mountain Dew and one can's super small and one can's super big or something like that. That wouldn't really make a whole lot of sense. So you want every single one to be congruent. So those would be examples in real life of congruent. So like, bolts and nuts, or cans of pop. Batteries is another one. So you would want all your batteries to be the same size when you open up a box of them. So if you get like AAAs, you go to put them in, whatever, your remote or something like that, and they're not all the same size, well, that wouldn't be really convenient to put them in your remote, right? So you're depending on their congruence, so it works for whatever you're doing. There's a couple other forms of the definition of congruent figures on that same page there. So it starts the same. Two figures F and G are congruent figures if and only if the image of F, and then it says under a composite of reflections. So all they changed between the first one and the second one there is they changed isometry to composite of reflections, but we know from the previous chapter that an isometry is a composite of reflections. So that's not really changing at all. They're just changing the wording a little bit, switching out isometry for composite of reflections. Same with the next one. The only thing they switch is instead of saying isometry, they actually list all four isometries out. So rotation, translation, reflection, and glide reflection, any of those three would work for that definition there because they all really mean the same thing. The next thing you might see here is congruence transformation. So it's a transformation that is a reflection or composite of reflections. Really, that's the same as isometry. So you could swap, anytime you see isometry, you could swap this phrase in congruence transformation. Okay, same as if you saw congruence transformation, that just means isometry. They're just interchangeable words. Next thing we've got is directly congruent and oppositely congruent. So directly congruent is they have the same orientation. Oppositely congruent would be they have different orientation or opposite orientation. So I'll draw you a little picture here. So say that's my shape. I take and I do a slide and I get that shape. Those would be directly congruent because they have the same orientation. Now if I took that shape again and I did a flip of it, like that, those would have opposite orientation because they would be going in different directions. So this would be directly congruent. An example of that would be like a slide. A reflection would be oppositely congruent. And you can go back to last chapter when we were talking about orientation, whether it's preserved or whether it's reversed. That'll kind of help you figure out if it's going to be directly congruent or oppositely congruent. So if orientation's preserved, it would be directly congruent. If it's reversed or switched, it would be oppositely congruent. Okay, so we've talked about some transformations that actually don't come out to be congruent figures. One of these would be a size change. So like say here this side was 6 and that side was 3, so we kind of reduced it down by 2. Those sides would not be the same, so that wouldn't fit our ABCD theorem of our distances of our sides being the same. So that's why size change would not be an isometry and would not be congruent. So you could say, if they asked you, why it's not congruent, you could say distance is not preserved. Okay, another one we didn't necessarily talk about that might come up would be shear. So shear is basically when you take a shape and kind of push it over like that. So this also would not be congruent because if we look at our angles here, you can see like that one there's a 90, but when I take and push it over, that angle's not the same. Same as that here's a 90, and that one's different from it. So since those angles don't match up with each other anymore, that's why that would not be congruent. So for this one, you could say angle measure is not preserved. Okay, so the only ones that are going to yield congruent are those 4 isometries that we talked about before. Okay, the last thing here we have equivalence properties of congruence. So if you flip to page 254, you've got reflexive, symmetric, and transitive. Those are really, really similar to the equality ones that we did before. So like when we had something equals itself, that was reflexive, and then when we had 2 things that we were switching around, that's symmetric, and transitive is the 3 things. The only difference is they put a congruent sign. The sign for congruent is an equal sign with a squiggle above it. So anytime you see that, that means congruent. So the only difference between the ones we did before with the equals and the ones we're doing now is that congruent sign in there. But really it means the same thing. Well, it means pretty close to the same thing, but reflexive, still something congruent to itself, symmetric, 2 things being congruent with each other switched around, and then transitive, 3 things being congruent with each other switched around. Okay, so really similar to what it was before. Alright, so that's it for notes, not very long notes. So you got page 255, 1 to 9 all, and then 10 to 18 even.